Today, we're going to calculate how to hit this frog using this projectile launched from this projectile launcher. Well, aloha everyone. Today, we're going to talk about projectiles launched at an angle. Now, it turns out it's pretty easy to figure out if you already know how to deal with projectiles launched horizontally. It's pretty easy to see the difference between that and a projectile launched at an angle. In fact, there's really only one big difference, and that is you have to figure out what the initial horizontal speed are and what the initial vertical speed is. If you're able to do that, the rest of it goes almost exactly the same way. So let's take a look here. Let's imagine we have a cannon type thing, sort of here. And let's say it is aimed not horizontally, but it's aimed at an angle here. Maybe this angle, as compared to horizontal, is going to be an angle of 20 degrees. And maybe this thing shoots with an initial velocity of, I don't know, let's call it 100 meters per second. And we want to know everything about this. How long does it take to get to the top? So number one. How long does it take to get to the top of its path? So, how long does it take to get to the top of its path? Number two, I want to know how high does it go? I want to know the total time of flight. And finally, I want to know how far away does it land? Okay, so in order to approach this problem, the first thing I want to do is I want to make a table of my values that I know. Oh, and by the way, I want to think only about either the rising section or the falling section. So this is similar to the vertical motion problems that we did a few weeks ago. So I'm going to look at first only at the rising section. And we're going to make ourselves a table of all the kinematic variables in both of the directions. So there is going to be a distance in the x direction, or displacement in the x, displacement in the y. V initial x and V initial y. A V final x and a V final y. An AX and an AY. And finally, time is the only variable we can use in both of those directions. So let's start by figuring out the pieces that we already know from the problem. Well, turns out there's precious little. Let's decide that we want to choose, to the right is going to be positive x, and upward is going to be a positive y. Well, we don't know how far this is going to go. We don't know how high it's gone. We don't know either V initial y or V initial x. But what we do have is this initial velocity at a strange 20-degree angle. So we need to break that velocity up into components along the x and y axes. What do I mean by that? Well, the initial velocity is going this way. Call that about 20 degrees. So the initial velocity is going that way at 100 meters per second. That means if I want to know the horizontal component of this velocity, it's going to be how fast is it traveling that way. And if I want to know the vertical component, I want to know how fast is it rising like so. So it turns out if this is V initial, this would be V initial x, and this would be V initial y. This is our angle of 20 degrees. So if you look at this triangle, you immediately realize that this is a trigonometry problem. This is the hypotenuse on the 100 meters per second side. The V initial x is the adjacent side, and V initial y is the opposite side. So it turns out if I want to find V initial x, I can use cosine to do that. What do I mean by that? I know that the cosine of the angle has to be equal to the adjacent side divided by the hypotenuse. In this case, it's going to look like this. The cosine of the angle is equal to V initial x divided by just V initial without any subscript on it, just for that 100, right? So now all I need to do to get V initial x is multiply by V initial on both sides. And I get V initial times the cosine of theta is equal to V initial x. So this is equal to 100 times the cosine, I guess that's meters per second, times the cosine of 20 degrees will give us our initial velocity in the x direction. So when I do this, I get 93.969 meters per second. Okay, so that is going to be my V initial x. I'm going to put that into my table over here. 93.969 meters per second. I know that. Then I'm going to find the initial velocity in the y direction. Over here, you can see that the initial velocity in the y direction is the opposite side. So I need something that relates the opposite side to either of the other two sides. I could use sine and I can use tangent. Either of them is fine since I know the two other sides of this triangle. However, it's going to be a little bit better practice to use tangent because this number, 100 meters per second, we assume is exact, or at least pretty close to exact, whereas this number right here, 93.969, has been rounded. And so there's going to be a little bit of rounding error. It's going to be a little bit better to use what's given in the problem because that will make our rounding error be a little bit less. It's not a huge deal, but it does make it a little bit cleaner. So I'm going to use the opposite side and the hypotenuse side. And if I remember my trigonometry correctly, I remember that sine of an angle is equal to opposite over hypotenuse. So looking at this, I realize that in this case, this is going to be equal to V initial y over V initial. So I'm going to multiply by V initial, and I will get V initial times the sine of theta is equal to the opposite side. Or I guess we'll just call that V initial y. Okay, this is equal to 100 meters per second times the sine of 20 degrees. And this is equal to, when I do this, I get 34.202 meters per second. Ooh. Meters per second. And I'll go ahead and input that into my table up here. 34.202 meters per second. Now that I have the initial velocity in the x and the y directions, I know a few other things. I know if I'm only looking at the rising portion of the motion, I know as that thing rises, it's still going to be moving horizontally, but at the top, it's going to stop rising and it's going to start falling. That means just for an instance at the top, the final y is going to be 0 meters per second. Remember, this is looking at the rising section only. It's not the whole thing. All right, since I picked upward as positive y, I know about gravity. And I know gravity is pulling it downward, so it's going to need to be a negative 9.81 meters per second per second. And over here, I also know the acceleration in the x direction, assuming there's no air resistance or wind or anything weird going on like a magnetic field. This is just going to be 0 meters per second per second. Okay. We have three things in one direction. That means we can solve for the other two if we want to. And question 1 is asking, how long does it take to get to the top of its path? So we want to solve for time that it's rising. So I look here and I say, okay, I've got v initial, I've got v final, I've got acceleration. I'm looking for time. That sounds to me like kinematic equation number 2, which says v final equals v initial plus a times t. These are all vectors. And to remind myself that I cannot mix these, since I have 3 things in the y direction but only 2 in the x direction, I can only use the y direction to solve this problem right now. So this is going to have to be applied in the y direction. I'm going to put little y's on each of these vectors to remind me that I can only use variables that are in the vertical direction to solve this. Okay, I'm looking for time. Let's solve for t. Solve for t. When I do this, I'm going to start off by subtracting v initial y. So it's going to be v final y minus v initial y, both vectors. Then I'm going to divide by ay, and that will give me t. Ay is a vector as well. And that will give me t. All right, so now all I need to do is plug in the numbers. V final y is 0 meters per second minus v initial y is going to be, what was it, 34.202 meters per second. 34.202 meters per second. Divided by an acceleration of negative 9.81 meters per second. We plug this into our calculator. And when we do that, we get 3.486. 3.486 seconds. If you're getting a negative number, it's probably how you're plugging it in. This 0 minus the 34 actually ends up with a negative number. So there's a negative number on top of this, and there's a negative number on bottom. Those negatives cancel to give us a time of 3.486 seconds. So we have just calculated the time it takes to get to the top is going to be 3.486 seconds. Now that we know this, we can plug this in and find number 2. How high does this projectile go? Well, in number 2, that's going to be distance in the y direction as it's rising. So, distance y for the entire rising time. Okay, so we look at this and we say, I need to find distance. There are 2 possible equations you can use. You can use either your kinematic equation number 3 or kinematic equation number 4. Either one will work. In this case, I think it's a little bit easier to use kinematic equation number 3 because we don't have to solve for d. D vector equals v initial vector times t plus 1/2 at squared. A is a vector as well. Remember, on each of these vectors, I want the distance in the y direction, so I'm going to put y's on each of these as well. Okay, all I need to do is plug in numbers here, and this is going to get a little bit long, but it's all right. Distance in the y direction, or displacement in the y direction, is equal to v initial y was 34.202 meters per second. 34.202 meters per second. Times our time we just calculated was 3.486 seconds. Plus 1/2 times a negative 9.81 meters per second for AY times a time we just did of 3.486 seconds squared. When I do this, dy is equal to 59.621 meters. If you didn't get that answer, check 2 things. The first thing to check is to make sure, did you use that squared? The second, is that negative? Those are the 2 most common mistakes. Okay, so 59.621 meters. Now that I have the distance in the y direction, or the displacement in the y direction, I can start thinking about the other pieces. Number 3, what is the total time of flight? Well, the total time of flight, in this case, since it's a flat surface, is going to be just doubled the time it takes to go up. So the total time of flight, all I need to do is multiply that time by 2. So the total time of flight is going to be equal to the time we just calculated, so the time it's rising, times 2. If it was different, if it was launched from up here, but it landed somewhere down here, we'd have to figure out the time it takes to rise, then the time it takes to fall, then add them together in order to figure out the total time of flight. Here, the time of flight is equal to the time it's rising times 2, since it's a flat surface, and this is equal to 3.486 seconds times 2 will give us, let's see, that's a 2, that's a 7, that is a 9.6 seconds. 6.972 seconds. Okay, we know the total time of flight now. So we need to figure out how long is, or how far away does this projectile land? Well, it's moving in the x direction the entire time. So we're not just looking at the rising portion now. Now we're looking at the entire thing, the total whole motion. So this is rising and falling in order to calculate how far away it goes. So if it's rising and falling, I'm going to use the total time of flight. So I'm going to have t is equal to 6.972 seconds. I also know I'm going to use v initial x here. I know v initial x was equal to, have to go back and look that up, 93.969. So 93.969 meters per second. I know v initial x, I know the time, and I'm looking for the distance in the x direction. And I know the acceleration in the x direction is going to be equal to 0 meters per second per second. That means that I know 3 of the things. I'm looking for d. I can use kinematic equation number 3 in order to solve this. That's going to be this one. d equals vi times t plus 1/2 at squared. X, x, and x, vector, vector, and vector. Okay, now that I have this equation selected, I know that my acceleration in the x direction is going to be 0, which means everything after this plus sign, that's all going to multiply to 0. So that's all gone. I don't need to worry about it. And all I need to do is plug in some numbers. Distance in the x direction, or displacement in the x direction, is equal to, my v initial is 93.969 meters per second. I'm going to multiply that times 6.972 seconds. And my displacement in the x direction is going to be equal to 655.237 meters. If you didn't get exactly that number, if you're off by a few numbers out here in these last digits, that's probably fine. That's probably just rounding error. I tried to keep my digits exact as I could. So even though I was writing 93.969, I actually used the number in the calculator, which was 93.9692620785991. And when I did that, I also used as close to the exact time as I could. And I do that in order to try to keep my rounding error from getting bigger. But if you were using the exact numbers that I was writing down, you probably got something slightly different, but it's not a huge deal. As long as you're very close to that number, as long as it's only in the last digit or two, it's probably perfectly fine. So now that we've seen how to deal with a problem like this, let's get back to our original activity. So the first thing we're going to do is we're going to fire a shot where the projectile launcher is aimed at a 0-degree angle. So first I'm going to make sure it's nice and level. Yep, that looks probably not perfect. A little bit of a tap there. Close enough. All right, I'm going to fire this projectile launcher at a 0-degree angle. In 3, 2, 1. I was watching very carefully where that projectile landed, and it turns out it was right in this area right here. So I put down a piece of paper. I'm going to fire it again just to see if it lands on that piece of paper. That should be good enough. So now that I can see where it landed, I'm going to take a piece of carbon paper and lay it down on top of this piece of paper. What that's going to do is it's going to make a mark every time that projectile lands on it. So one that's very easy to see. And then we're going to fire it off 3 or 4 more times. So now that we've shot this off 5 or 6 times, I'm going to remove this piece of carbon paper, and we will see that each time the ball landed, it left a mark. I'm going to measure the distance from the projectile launcher to where each of these marks is horizontally. While I'm at it, I'm also going to measure the distance from the ground to the bottom of this opening where the projectile comes out of. So here are the measurements I've taken. I found the distance to each, the horizontal distance to each of those black dots, and they're listed on the left. I also found the height, which was 1.21 meters. And the average distance in the horizontal direction was 2.029 meters. So the first thing I'm going to do is I'm going to calculate the time it takes for the ball to drop to the ground. Since we're firing horizontally, we know some things. So this is for the horizontal launch. It's going to look something like this. Here's my projectile launcher, and it's up on top here, like that. And when we fire it, it follows this parabolic trajectory, and it lands down here. And we know this distance, on average, is 2.029 meters. We know this distance is 1.21 meters. And yeah, that's, oh, well, we know the angle here. Angle is 0 degrees right now. Okay, so we're going to start by making our table of our kinematic values. So we're going to have distance in the x direction, well, displacement in the x direction, displacement in the y direction, v initial x and v initial y, v final x and v final y, ax and ay, and t. All right, and this is equal to, let's see, distance in the x direction was 2.029 meters. 2.029 meters. Distance in the y direction is 1.21 meters. I don't know v initial x yet, but I do know v initial y is going to be 0 meters per second since we're launching horizontally. I don't know either the final velocities, but I do know both of the accelerations. Ax is going to be 0 meters per second, and ay is going to be equal to gravity I haven't chosen the sign convention yet. Let's make this way positive x. And I'll tell you what, let's make upward positive y. So there's two things here. This should be negative 9.81 meters per second. But you'll also notice that since the ball starts at the top and drops to the bottom, my displacement is going to be downward as well. So we need a negative on that 1.21 meters. Okay, we can find the time. And we can find the time using the y direction here. So using the y direction, I can find time. And so I'm going to use kinematic equation number 3. Kinematic equation number 3 says d equals VIT plus 1/2 AT squared. That's a vector, that's a vector, and that's a vector. And we're going to use the y direction here, so dy, VIY, and AY. Now that I have this, I'm going to solve this for time. I know v initial y is 0, so this piece goes away. And I can solve this. I multiply by 2. It's a dy here. I divide by ay. And I square root is equal to t. So this is equal to the square root of 2 times dy is negative 1.21 meters divided by negative 9.81 meters per second. This is equal to a time of 0.497-ish, let's call it, seconds. All right, so there is our time that it takes for this thing to drop, 0.497 seconds. Now that I know that, I have 3 things I can use in my x direction, which means I can solve for v initial x. So let's solve for v initial x. I'm going to use, looks like it's going to be kinematic equation number 3 again. Only this time it's going to be in the x direction. Distance x is equal to, displacement x, is equal to v initial x t plus 1/2 ax t squared. All right, so I know ax is 0, so this entire piece is going to be gone, and we're going to be left with dx equals vix t. I'm going to solve this for v initial x, which is going to give me this, dx over t equals v initial x. This is going to be equal to my distance in the x direction on average, 2.029 meters, divided by, my time is 0.497 seconds. That should give me v initial x, and that is equal to, I get 4.085 meters per second. Give or take, it's I used exact numbers instead of rounded numbers when I did that, so it might be a little bit different from what you get if you're going through the numbers with me, but I get 4.085 meters per second as our launch velocity. So now we're going to take this whole thing and we're going to rotate it. Instead of launching horizontally, we're going to launch at a 28-degree angle. So now our diagram looks like this. That's a little bit high for 28 degrees, but just pretend it's all right. So here's my launcher. It's going to launch. That's terrible. Let's try that again. It's going to launch like this. Pretend that's 28 degrees. We know it's not, but figure not drawn to scale. 28 degrees right here. Okay, so if that's a 28-degree angle, this is going to be the same initial velocity of we just found it, what was it? 4.085 meters per second. Okay, and we are going to decide how far this thing is going to go. where we need to place that frog in order for this to work. Because this thing is up on top of here, and it's going to go boom and land somewhere over here. So we need to figure out a bunch of things. The first thing we need to figure out are the x and y components of that initial velocity. What are v initial y and v initial x? So I can do this. V initial x is equal to, we learned from earlier in the lesson, it's always going to be equal to v initial times the cosine of the angle. So this is equal to 4.085 meters per second times the cosine of 28 degrees. Likewise, to find v initial x, or v initial y, that's going to be v initial times the sine of the angle. So this is going to be 4.085 meters per second times the sine of 28 degrees. All right, plugging these into the calculator, I get 3.60, call it 7 meters per second for v initial x. And for v initial y, I get 1.917 meters per second. So now we can find the time to the top. Before I do that, I'm going to make myself my table that I like to make. So d in the x direction, d in the y direction, v initial x, v initial y, ax, no wait, let's do v final. V final x, v final y, ax, ay, and time. And we are looking at the rising section only at first. So as we're rising, let's plug in some numbers here. We do not know the distance that it's going to rise, but we do know v initial y and v initial x. So v initial x was 3.607 meters per second, and v initial y was 1.917 meters per second. I know acceleration y, I'm going to call this way positive x, and I'm going to call upward positive y. So that means acceleration in the y direction is going to be a negative 9.81 meters per second. Our time is going to, we don't know, ax is going to be 0 meters per second. And we know one more thing. We know if we're looking at the rising section only, that means the y velocity there at that top point is going to be 0. So v final y is going to be 0 meters per second. From this, we should be able to find time. So the time to the top. In order to calculate that, I'm going to use the y direction, and I'm going to use kinematic equation number 2. Which is going to say v final equals v initial plus a times t. These are all going to be in the y direction. And I'm going to solve this for t. So t is equal to v final minus v initial divided by a. Vector, vector, vector. And these are all in the x direction. No, in the y direction. All right, this is equal to v final y is 0 meters per second minus v initial y is 1.917 meters per second, all divided by acceleration y is negative 9.81 meters per second. When I do this, I get 0.195 seconds. So it's rising for 0.195 seconds. Let's find the distance to the top. In order to do this, I can use kinematic equation number 3 is probably the easiest one. So kinematic equation number 3 is going to say dy equals v initial y times t plus 1/2 ay t squared. Vector, vector, vector. And this one, we just have to plug in straight. There's nothing we can do about it. dy is equal to, v initial in the y direction was 1.917 meters per second times a time of 0.195 seconds plus 1/2. Ay was negative 9.81 meters per second times t squared is 0.195 seconds squared. For this, I get dy is equal to 0.187 meters. So that's how high it's going to go when it rises. But if you look at our diagram, that 0.187 meters only refers to this much of it. It doesn't refer to the whole distance because now the bottom has dropped out under it since we launched it from the edge of the counter. So because of that, we're going to have to add that in the falling part. So yeah, let's deal with the falling part now. So when we are falling, so this is not the rising part, this is the falling part. So now we're looking at when we're up at the top of our trajectory, and it is going just that much of the problem. So we've already done the part where it rises here. We're only looking at the part where it falls now. Okay, so let's make some new variables. Distance in the x direction, distance in the y direction, v initial x, v initial y, v final x, v final y, ax, ay, and t. Okay, well, it turns out the x direction isn't really important to us right now anyway, so I'm just going to kind of ignore it for the moment. And I'm going to solve this entirely in the y direction, since the horizontal motion does not cause problems or does not change the motion in the vertical direction. So I know that my distance in the y direction, well, it's 0.187 meters higher than the counter. So we need to add the counter's height in as well. And we had that way back up here somewhere. It was 1.21 meters. So I need to add that 1.21 meters to this problem as well. 1.21 meters is equal to, I get 1.397 meters. I know my v initial in the y direction as it's falling is going to be 0 meters per second, because right here at this point, it's not rising, it's not falling, it's 0. I know that my acceleration in the y direction is negative 9.81 meters per second, which means I can find the time it takes for it to hit the ground. So, sounds to me like kinematic equation number 3 again. Kinematic equation number 3 is going to say d equals vi t plus 1/2 a t squared. And I know that v initial in the y direction, these are all in the y direction, v initial y is going to be 0, so that piece is going to go away. I'm going to solve this for t, so this is going to be dy multiplied by 2, divide by ay, square root is equal to t. So this is equal to the square root of 2 times 1.397 meters divided by negative 9.81 meters per second. Ooh, something careful I need to look at. Look at the displacement here. I'm going from here to here, which means my displacement is downward, which means that I need a negative sign on this because I already chose upward as positive. So we need a negative sign right here as well, which is going to solve our problem with imaginary numbers, and we're going to get t is equal to 0.53, let's make it a 4 seconds. 0.534 seconds is going to be the time it takes for it to fall. So now we need the total time of flight. Well, this is easy. Just add the rising time plus the falling time. So it's going to be 0. What was my rising time? 195 seconds. 0.195 seconds plus 0.534 seconds is equal to, I get 0.729 seconds. By the way, like I said, I'm using exact numbers here every time I use the calculator. So if you're seeing a little bit of weird rounding error creep in places, that's fine as long as your answer is very close to mine. It should be perfectly fine. Okay, so it's in the air for 0.729 seconds. So how far is it going to go? Well, I can use kinematic equation number 3, only this time in the x direction. So the dx, displacement in the x direction, is equal to v initial x times t plus 1/2 ax t squared. All right, I know this piece is going to be 0 because ax is 0. So displacement x is equal to v initial x, we solved right way up here somewhere, 3.607 meters per second. 3.607 meters per second times, well, which time do I use? The time it's rising, the time it's falling, or the total time of flight? Well, if I want to know the entire distance it's went, I need to use the entire time. So I'm going to use the total time of flight here to figure out the entire x distance. If I wanted to figure out how far it had gone to here, so what this displacement was, I would use the time it's rising. If I wanted to find out how far it goes in this falling part here, from there to there, that would be the falling time. But if I want to know the entire distance it's going to travel, I'm going to use the entire time, 0.729 seconds. And when I do this, I get, let me see if I can find that velocity. I get 2.63 meters, or 2 meters and 63 centimeters. So now I'm going to take this frog and I'm going to place him at 2 meters and 63 centimeters. I'll center him right about there. Kind of try to line him up with the other dots. And let's see what happens. So that's really all there is to it about projectiles launched at an angle. Mahalo for watching, and see you next time.